Another really important application of our growth model, our growth and decay model, are compound interest and continuously compounding interest. Now, how we run into these particular formulas we'll get into separately. But here are the models, and we can see that, for example, our continuous compounding interest is, in fact, a, uh, a population growth model. If we think about it, it goes in the form y equals c times e to the kt, only in this case, a couple little things, right? If we look at how this model is constructed, our initial amount, P, that's what we call our principal. That's the amount that we invest, right? So that's what we invest. R is our rate of growth. Well, in this case, that's an annual savings rate, especially if we put our time T in years. All right. And of course, A is the accumulated amount that we get after those T years. For the compound interest formula, just a couple other things, right? Continuous compound interest assumes that we're just simply gaining interest continuously every day of the year, every hour, every second, and so on. In compound interest, we know that if you have a bank savings account, for example, you earn interest once every month, or you might earn interest once every quarter if you have certain thrift savings plans or something like that. So, compound interest, we say n is the number of compoundings per year, right? So that's the number of times we compound per year. Right? So if we say monthly, n is 12. If we say quarterly, n is 4, and so on. And of course, R is our rate. So everything else here is the same, right? So that's the only thing that really changes right here for our compound interest model. We'll talk about both. All right, let's assume that we've got a continuously compounding interest model, right? So that's our answer for A. We're going to use the model that says A is equal to P e to the RT, right? And we're told $18,000 is invested at 5.5% in a continuously compounding interest savings. How long does it take it to double? Well, what are we saying right here? Well, if we look at the given information, we're told that our initial amount, that's always our principal, is $18,000. Now, if you were to think about it, we could put 18,000 in for A and let T equal 0 and solve for P, but P would be 18,000. Of course, our rate is given as a percentage. Now, we do want to be careful right here. When we use these percentages, we're going to use the decimal form of this, right? So 5.5% is 0.055. All right, so we're going to work this out. How much should our account be, right? Well, our account, right, what we're going to accumulate is twice the amount that we started with, right? So we want to end up with double our money. That's $36,000 here. So what would that mean? Well, if we make the substitution, that means $36,000 is going to be the result of taking $18,000 as our principal and multiplying it by e to the 0.055 times t. And, well, then solving for t. Well, that's not too bad, right? Because if we divided both sides by 18,000, we're going to get 2 equals e to the 0.055 times t. And of course, specifically, we would take the natural log of 2 to get our t term by itself. So 0.055 times t is the natural log of 2. So we would take natural log of 2, divide that by 0.055 in this case. That's going to give us our time, and that will be approximately, I came up with 12.6027 years. Now, of course, we're not that precise with our time. This is about 12 years and 7 months, right? So 12 and a half years, a little bit more than that. So we could go with that. But let me just make a quick observation about this kind of problem. It didn't really matter how much we started out with, right? You see that, I hope. If we have an account and we're going to look for it, how long it takes for it to double, right? We can actually work that out using our model, right? Whatever our rate R is, if we want it to double, right, that means we want to end up with 2 times whatever our principal is. And so we could have worked this out and said, well, okay, that means that 2 would have to equal e to the RT, which is the natural log of 2. Notice we ended up with natural log of 2 is equal to r times t. And so the time to double your money in a continuously compounding interest account is going to be the natural log of 2 divided by whatever that rate is. That's kind of cool. That means that we could always just substitute right in and find that amount of time. Okay, so now let's talk about this second example, right? How much must be invested at 6% interest, compounded monthly, so that $1 million will be available after retirement after 40 years? Well, now this is just a single, remember, this is just a single, we put in some amount of money and we'll have $1 million after 40 years. Well, how much would we have to put in? All right, well, let's work that out. If we're interested in 6%, right, what will that do? Well, okay, we're going to use our first model up there. And we're told that this time we want to end up with $1 million. So A is equal to 1 million. Okay. So we're asked, well, how much must be invested? So we don't know what our principal is, right? We're going to have to work that out. Well, what else do we know about this model? Well, in this model, we know that our rate is going to be 6%, so that's 0.06. And we have to say, well, if it's compounded monthly, that means n is equal to 12. And t, given in years, is going to be 40. So making our substitutions, we're going to find this. 10,000, sorry, 1 million, not 10,000. I want to get $1 million. 10,000, chump change, right? No. 10,000 is a pretty good amount, too. All right, P, I don't know what that principal is, but I know it's going to be multiplied by 1 plus 0.06 divided by 12 raised to the n times t, so that's 12 times 40. Oh my gosh, this is just going to be a straight up division problem, right? Because if we work this out, our $1 million is going to be equal to the principal times, let's see, I work this out, 0.06 divided by 12. That's 0.005. So this is 1.005 to the 12 times 40. That's 480, right? So if we're going to solve for our principal is just simply going to be that $1 million divided by 1.005 to the 480th power. All right, now you can try this out on your calculator yourself. See if you get the same thing. Pause for a minute and see what you get. Well, if I work it out decimal-wise, here's what I got. I got 912. Wow, that's a terrible looking 2 there, Professor People. Let's try that again. 9, 1, 2, 6, 2. Copying digits and looking at the same time doesn't work. 0.07876. Well, of course, you know, this is money, right? We need to put this in terms of dollars and change. So what we should write is that the amount that we have to invest, if we're going to do this correctly, should be $91,262.08 if we want to make that $1 million mark in this account. All right. Well, hey, enjoy your $1 million.